All right, guys, Mr. Antonucci here, and in this video, we're going to do a deeper dive into related rates. By way of review, we're going to look at the guidelines real quick. First thing when doing related rate problems, you want to identify your knowns and unknowns, sketch and label a diagram of the situation if that's possible. Second, you want to write your equation that relates the quantities involved. Third, differentiate both sides with respect to time. And fourth, plug in your known values, solve for your desired rate, and always make sure to include the units on your answer. First, we're going to look at some perimeter, area, and Pythagorean type problems. The length of a rectangle is increasing by 2.5 inches per minute. We want to write that down as dl dt equals 2.5 inches per minute. The width remains constant 3 inches. That means that the width is 3 inches. Since it's constant, the rate of change of the width is going to be 0. So it may be helpful to write that down. How fast is the perimeter changing? So we want to know what is dp dt when the length is 10. And then it also asks for the area separately. So if we draw a little diagram here, the length and the width, we know the length is going to be 10. We know that the rate of change of the width is 2.5. Now, we have to write an equation that relates the quantities involved. So that would be perimeter here, which is 2L plus 2W, and then differentiate that with respect to T. dp dt equals 2 dl dt plus 2 dw dt. Now, this term is going to go away because the rate of change of the width is 0 because the width is constant. So if we plug in our values, 2 times dl dt, 2.5, that's going to give us 5, and the units would be inches per minute. Now let's do the second part, the area. We know the area function is length times width. So the rate of change of the area, we would have to use the product rule here. So the derivative of the first, dl dt, times the second, plus the derivative of the second, dw dt, times the first. Now, dl dt is 2.5 times the width. We know the width is 3. And then the dw dt is equal to 0. So that term is going to go away. 2.5 times 3 gives us 7.5, and the units here would be inches squared per minute. And if you think dA dt, the units for area, inches squared, over dt, units for time, minutes. In this example, a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. So we know the shape we're dealing with here is a circle, and the radius of the outer ripple is increasing at a constant rate of 1 foot per second. So I'm just going to label the radius here, but that's not what the 1 is. That's the rate of change of the radius, so that's dr dt equals 1 foot per second. When the radius is 4, so when r is 4, at what rate is the total area of the disturbed water changing? So we want to know what is dA dt. So first we need an equation that relates the quantities involved. So the area of the circle, we know pi r squared. And then we differentiate that. Don't plug the r in yet until after you differentiate. So it's going to be 2 pi r dr dt. And we know to use implicit differentiation here because we're differentiating with respect to time. Then we plug in what we know. So it's 2 pi times 4 times dr dt, which is 1. So we would have 8 pi feet squared per second. If we round to 3 decimal places, that's going to be 25.133 feet squared per second. So here at 2 p.m., a car A is traveling to the west towards Columbus, Ohio at a speed of 60 miles per hour. So I'm going to draw a little diagram here. This is going to represent Columbus. And here is car A. It's traveling towards Columbus at a speed of 60 miles per hour. So that gives us dA dt. But if A represents the distance that the car is from Columbus, then that rate is going to be negative because that distance is going to be decreasing. Car B is traveling north of Columbus, Ohio at a speed of 50 miles per hour. So it's moving north at 50 miles per hour. So that gives us dB dt is 50 miles per hour. At this time, car A is 300 miles from Columbus, while car B is 400. So we know A is 300 and B is 400. Find the rate of change of the distance between the two cars at 2 p.m. So really, we're looking for the distance right here, and we want to know the rate of change. So dd dt. So an equation that relates these quantities would be the Pythagorean theorem, because we have the sides of a right triangle, essentially. So this would be d squared equals a squared plus b squared. Now, all of these quantities are changing, so we can't plug the 300 or the 400 in yet, or even solve for d. So we would differentiate everything with respect to t. So this would be 2d dd dt equals 2a dA dt plus 2b dB dt. Then we could solve this for dd dt. So I'd divide everything by 2d, a factor of 2 would cancel, and we'd have, and then we could plug in what we know. A is 300, dA dt is negative 60, B is 400, dB dt is 50, and we don't know the value of d, but we can use the Pythagorean theorem. If we plug 300 in for A and 400 in for B and solve for d, well, we would get 500. This is also a 3, 4, 5 triangle multiplied by a factor of 100. So it'd be 300, 400, 500. So we're going to divide by 500 here. This comes out to 4 miles per hour. So the distance between the cars is increasing at 4 miles per hour at this moment in time. Another type of related rate problem that comes up often is ones dealing with volume. So a spherical balloon is inflated at a rate of 10 cubic meters per minute. So that's telling us the rate of change of the volume. So we'll write that down, dV dt equals 10 meters cubed per minute. And we know we're dealing with a spherical balloon, so I'm going to draw a circle and label the radius right there. We want to find the rate at which the surface area of the balloon is increasing. So that's going to be ds dt, where s stands for the rate for the surface area, when the radius is 3. So we know the rate of change of the volume, and we want the rate of change of the surface area. Surface area formula is 4 pi r squared. So ds dt is going to be 8 pi r dr dt. We know r is 3, so this is going to simplify to 24 pi dr dt. The problem is we don't know dr dt, and we haven't used all the information that was given. We also know that the rate of change of the volume. So what we can do is try with the volume formula. So the volume formula of the sphere is 4/3 pi r cubed. And dV dt is going to be 4 pi r squared dr dt. And thankfully, we know the rate of change of the volume and we know the radius. So we know this is going to be 10 equals 4 pi times 3 squared dr dt. And then we can solve this for dr dt. We'd have 10 over 36 pi. So we can substitute that in here. So 24 pi times 10 over 36 pi. The pi's will cancel and everything will simplify down to 20 thirds. And so our final answer, I'm going to put it in a box right here, would be 20 thirds meters squared per minute. But the units work out for the rate of change of the surface area. Surface area units are going to be meters squared. The units for time are minutes, so it's meters squared per minute. Here's another volume one. The radius r of a sphere is increasing at a constant rate of 2 centimeters per minute. So this is going to be dr dt. At the instant the surface area becomes 64 pi centimeters squared, so that gives us the surface area. Find the rate in cubic centimeters per minute at which the volume of the sphere is increasing. So we want to know dv dt. Again, you have a sphere, the radius. So we want to know what the rate of change of the volume is. So let's get the volume formula, 4/3 pi r cubed dv dt. It's going to be 4 pi r squared dr dt. Now we know what the rate of change of the radius is, but we don't know what the radius itself is. However, we do know that the surface area is 64 pi. So we know that 64 pi is going to equal 4 pi r squared, because that's the formula for the surface area of a sphere. So divide by 4 pi and you have r squared equals 16. So this tells us that r is 4. So you have 4 pi times 4 squared dr dt is 2. So this comes out to 128 pi. And the units would be centimeters cubed per minute. Again, think of it in terms of units for volume over units for time. So one more volume problem. Sand is poured into a right circular cone at a rate of 16 cubic feet per minute. So the cone is going to look like this. And then inside of it is a right triangle like that. If it's being poured at a rate of 16 cubic feet per minute, that's dv dt. That's the rate of change of the volume. And since it's being added, it's going to be positive 16. If the height and radius of the cone are equal, now this obviously is not drawn to scale, but there's the height and radius, and we know that the height is equal to the radius. How fast is the height of the cone changing? So that's dh dt equals, I don't know, when h equals 7. So let's get the volume formula for the cone. Volume is 1/3 pi r squared h. We know that h equals r. And since we're asked for dh dt, we're going to get the entire volume formula in terms of h. So if r is equal to h, then this would simplify to 1/3 pi h cubed. Then dv dt is going to be equal to pi h squared dh dt. And at this point, we could either solve for dh dt and then plug the values in, or plug the values in and solve. I sometimes like to plug the values in first. So if I divide here, dh dt is going to be 16 over 49 pi. 7 squared is 49, and we would divide by that. The units here, since it's rate of change of the height, would be feet per minute. Again, units for height over units for time. Another situation that comes up is rate of change that involves either angles or similar triangles. Now we have that same car situation, but this time, if you read it carefully, we want to know at what rate is the angle between car A and Columbus and car B. So A is like the vertex of that angle. We want to know what's the rate of change of that angle. So that is going to be d theta dt. We know that the opposite side of that angle, which is B, is 400. And we know the adjacent side, which is A, is 300. Well, the trig ratio that we know, because we're dealing with angles, that's a hint that we should use a trig ratio, is going to be B over A, opposite over hypotenuse. Now, we don't plug the 4 and the 300 in yet because those values are changing. We're just looking at it the instant those values are 400 and 300. Then what we would do is differentiate everything with respect to t. Now we have three variables here. We have theta, b, and a. All of those are changing. So the derivative of tangent is secant squared theta d theta dt. And b over a, we'd have to use the quotient rule. So derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Now, secant theta is hypotenuse over adjacent. In this case, the hypotenuse is going to be 500. We solved for it in a previous problem, but also this is a 3, 4, 5 triangle. So we would have 500 over 300, which simplifies to 5/3. So we're going to substitute everything into this expression here. Secant is 5/3, so secant squared would be 25 ninths d theta dt equals dB dt, which is the rate of change of car B, 50, times A, which is 300, minus the rate of change of A. Remember, it was moving closer to Columbus, so its distance is decreasing, so the rate of change would be negative, times B, which is 400, all over A squared, which is 300 squared. And then if we solve this for d theta dt, you would get 39 over 250. And here, the units would be radians per hour. This one's going to involve similar triangles. A rectangular swimming pool, 10 meters long and 5 meters wide, has a depth of 3 meters at one end and 1 meter at the other end. So let's just look at what's going on here. So we have the pool, it's 1 meter at one end, it's 10 meters long, and it's 3 meters at the other end. So this is what a side view of the pool would look like, and it's 5 meters wide this way. If water is pumped into the pool at a rate of 0.3 cubic meters per minute, so that's dV dt, that's the rate of change of the volume. At what rate is the water level rising? That we want to know what is dH dt when it's 1.5 meters deep at the deep end, so when H is equal to 1.5. So if we imagine the water level right here as rising up from the bottom as it's poured in, until it gets to 2 meters deep, it's always going to make a triangle like that. So really we have two similar triangles, one inside the other. We know that bigger triangle has a length of 10 and the height is going to be 2, because when it's up to the top there, it's only going to be 2 meters deep because the next meter is going to be filling up that rectangle at the top. So the portion that is actually filled in has a height here and a length here. Now we can set up the volume of the pool. So the volume is going to be 1/2 length times width times the height. We know that the width is always 5 because no matter how deep the pool gets, it's still going to be 5 meters wide. So we could do 5 times L times H. But from this diagram over here, we know that 10 over 2 equals L over H. So L is equal to 5H. We could substitute that in to get the volume formula all in terms of H. If I plug 5H in for L, this would simplify to 25 over 2H squared. And that's the volume formula in terms of H. Now, I want to know at what rate is the water level rising. I would have to differentiate that. So dV dt is 25H times dH dt. Rate of change of the volume is 0.3. I know the height is 1.5. And I don't know dH dt. But if we solve that for dH dt, we would have 1/125th, and this would be meters per minute. All right, last one here. Bill is 6 feet tall and is walking away from his street light at a rate of 4 feet per second. If the street light is 15 feet high, at what rate is this shadow growing? So let's set up a picture here. Here is the street light. It's 15 feet tall. Here is Bill. He's 6 feet tall. This would make a right triangle, and this is his shadow right here. We'll call that distance x, and this distance here, y, is his distance that he is from the street light. Now, if he's walking away from the street light at 4 feet per second, that means the distance y is changing at a rate of 4 feet per second. We want to know at what rate is his shadow growing. That's dx dt. Again, we have similar triangles here. So we know that 15 over this entire side of the triangle, which is going to be y plus x, is going to be equal to 6 over x. If we cross multiply, we would have 15x equals 6y plus 6x. And then simplifying that a little bit, combine the x's, you would have 9x equals 6y. So y equals 9/6 x, which would be 3/2 x. And then if we differentiate that, dy dt is equal to 3/2 dx dt. We know that dy dt is 4. So 4 equals 3/2 dx dt. So if we solve this for dx dt, we would get 8/3, and the units there would be feet per second. And that's it. His shadow is growing at a rate of 8/3 feet per second at this moment. Well, guys, that's it for related rates. Hope that video was helpful to you. Take care.